Hello everyone, my name is Georgios Trichopoulos. Welcome to the Electromagnetics Pathways presentation. So today I'm going to go over some of the basic stuff about the pathways that is focused on electromagnetics, as the title says here. We'll see, what is the field of electromagnetics, what we are going to be, working on, what are the related courses, why do we care about electromagnetics, what are the opportunities for you, and then we're going to close with some questions. I know there's going to be some pizza, so whenever the pizza comes, we're going to take a break, I guess. Electromagnetics. So what is this about? I know some of you might have, some idea. So electromagnetics is essentially to study the effect of charges, right? Either charges that are just static, they don't move, or charges that actually move around or oscillate. So the electromagnetics is, concepts that come from physics. You've probably seen them already in physics. And they are described by a set of theory, which is called the electromagnetics equation, the Maxwell's equations. So the Maxwell's equations are the more general form, and they also take some more specific form where we call them approximations. This is like the circuit theory. Circuit theory is based essentially on Maxwell's equations, optics, Kirchhoff's laws that you see in circuit theory and stuff like that. So, Maxwell's equations come from this famous guy, James Maxwell. He was the one that started working on this theory. Originally, the equations were actually 12. But now we're only working on these 4 equations. These are the 4 fundamental equations, the Maxwell's equations as we call them. So these equations relate electric field, magnetic field, currents, and charges. So they give the interrelationship of all these quantities. So everything we do is essentially based on that. So what do we care about electromagnetics, right? How can electromagnetics help us? First of all, EM, so a lot of the time we call electromagnetics EM, just as a short, is essentially the basis of electrical engineering. So everything you're going to do in electrical engineering is essentially based on these 4 Maxwell's equations. It just sometimes is an approximation of that, so you don't really need to go and use these complex equations. You can use simpler equations, like in circuit theory, as I said before, either analog circuits or even digital circuits. Everything is really based on these 4 equations. Now, having these equations, we can do some very interesting things. We can design antennas, RF microwave circuits. These are very high frequency circuits, fiber optics. In general, we can design both wired and wireless communication systems, for ultra wideband and very fast internet. Electronic packaging, design how circuits are designed when we actually package them and put them in electronics. Now, I want to give you a more specific example here, like more recent development on the area, on one of these applications actually. And this comes from wireless communications. So you might have heard already from the news that there's more and more spectrum available. Spectrum is, the frequencies that are out there and that haven't been utilized yet. So you see that right now the systems that we're using, the wireless system that we're using, utilize frequencies up to a few gigahertz, 3-4 gigahertz, like Wi-Fi is 2.4 gigahertz, or cell phones is, a little bit less, 1 to 2 gigahertz. But the trends are to actually use much higher frequencies than what we use right now. So 24 gigahertz, 24 to 28 is the next band that's been actually, officially allowed, 37 to 40, 64 gigahertz to 71, and even higher. Why we do that? Because we need more and more bandwidth. What we have is not enough right now. You might have heard of the Internet of Things. This is like devices that are actually going to always be connected on the Internet. So this means you're going to have so much more devices that really need access to the Internet. They will need information, so this means a lot of traffic. And we as users, we tend to use more and more data. Like we have images, now we have more and more video streaming. So all these things really need much more speed. So going to more spectrum, using more of the spectrum that's out there is really is really necessary. So that's what we call 5G. It's kind of the next generation in wireless communications. We have 4G that we're using now. It's really the mainstream, but 5G or even future generations are really needed. There are already actually devices that have been that start becoming commercial and available for that. But this comes with many challenges, and we as engineers are here to solve them. You as future engineers will be there to solve them. These are really what is needed when you go in very high frequencies. Now, the concept of having one antenna here, a circuit there, all these distributed components is not anymore valid. You go higher frequencies, you need everything really in a tiny chip. So this chip that you see there has not one antenna, has several tens of antennas. It has an extremely high frequency circuit, both analog as well as digital, all of them in one very small package, one very small circuit, which is actually integrated on your mobile devices. So these future frequencies will allow us to do now what we call directive communications, right? So right now our cell phones just radiate signals everywhere. In the future, when we have so many antennas, we'll be able to have a very narrow beam that goes and focuses in a specific base station, so we can have much more bandwidth. But this comes with challenges again that go all the way from antennas to amplifiers to what we call splitters and phase shifters, devices that work in very high frequencies. Whenever you see very high frequencies, it means that you have very complex propagation phenomena. And this can be described by Maxwell's equations, as I said in the beginning. Now, and this, again, wireless communications is one of the many applications that you as an electrical and specifically as an electromagnetics engineer will have to face. But it's one of the biggest, needs out there. Now, what do you need to become a successful engineer in electromagnetics? You need a solid, good background in mathematics, physics, as well as circuits, right? So these are really very, very key requirements. And engineers, you probably have heard before, we're not just technicians, right? We're here to see a bigger picture of a problem, design solutions, work with other disciplines, not just electrical engineers, but other disciplines to provide solutions to different challenges. So now to become more specific about what courses do you need once you're here at ASU, and what of these courses are related, and what are the prerequisites. So prerequisites are obviously, you start from physics 2 as well as the lab on physics 2, which give you the very first concepts in electromagnetics. What is a static electric field, what is a static magnetic field, what is a charge, what is the currents. You start with these concepts. Then you have the circuits 1 or EEE 202, which is the basic theory of circuits, Kirchhoff laws, and then you go to 241, which is now when you actually get into the fundamentals of electromagnetics. Again, there's going to be some overlap between 241 and physics in terms of what is electric field, what is a charge, right? But in 241, we go more to the fundamentals. We work now a little bit more between the physics and the math. So 241 is essentially when you start really being exposed into the theory of electromagnetics. So that's the very first course that you see. It's offered both fall and spring. And what is this about? This is about static and time-varying fields, as I said before. So like I would say 60–70% of the course you do static electric field, static magnetic field, and at the end of the course you start discussing about fields that start changing with time. So oscillating electric fields. When a charge moves up and down, right, that creates an oscillating electromagnetic field. That's when the electric and magnetic field become actually one, interrelated. And this is all, this is where the Maxwell's equations come about. Now, after the 241, we offer the 341. So for the 341, obviously, 241 is a prerequisite. So 341 is all about Maxwell's equations, varying, very fast varying fields, propagation of a signal in a transmission line, propagation of signals in free space, how antennas work, how antennas propagate the signals, how they receive the signals, all these concepts. 341 has also a lab component. It's a 4-credit course, 341. And then you go to the more senior courses, right, which is a 400 level courses. Here we have 443, which is Introduction to Antennas, essentially. So you learn all about so by the way, here, there's always some overlap between these senior courses and the 341, right? 341, you get some idea about the more advanced topics. But here, when we talk about antennas in 443, you talk about the basics, but you also explore different types of antennas. Antennas, like antennas that you have in your cell phone, or computers, or bigger antennas, antenna arrays, this type of concepts. And microwaves, 445, microwaves is essentially circuit design for very high frequencies, right? In circuits, as you're going to do, or you may have done already, the circuit is always much smaller than the wavelength, right? The wavelength is what is the length of the period of the RF wave. When your circuit is smaller than that, then you can use circuit theory. But the problem becomes when your signals are so fast, they oscillate so fast, that the wavelength becomes comparable to the size of your circuit. Circuit, antenna, whatever you have there. So at that point, that's when you have to use a theory that is covered in microwaves engineering, right? So there we talk about topics of impedance matching, how you do measurements of these RF signals, right? We talk about these high frequency devices and sources and etc. And then we have 448, fiber optics. As the name says, it introduces you to the concepts of using waveguides and transmission lines for visible light. Visible light is another type of electromagnetic wave, right? It's just a much higher frequency. But visible, or not just visible, infrared, all these type of radiations are used for communications or even for sensing. So how do you manipulate these signals? So fiber optics is dealing all about that. Like you have electro-optical devices, you have waveguides that we call them, fibers. So all these basic concepts are in 448. Now, beyond that, beyond the undergraduate, curriculum, there are a lot of courses offered for like graduate courses. So I'm just going to go very briefly over this. These are obviously more specialized courses. So you want to take a break maybe, or you want me to?
That's okay with you, Professor.
Okay, so let's take a break now.
Short pizza break.
And then we'll continue with the rest of the slides. So 241 is probably the course where you're going to use mostly math, right? Because 241 is a little bit more abstract. All the rest of the courses after 241, like 341 and all those 400 levels, they become much more practical. So you still use math, but they're a little bit more applied, I would say. Right? So some people might take 241 and say, "Oh my God, this is like." I see when I teach 241, like people get scared with it because, "Oh, is this EM? Okay, goodbye." But it's. I mean, again, it's the first, introduction into electromagnetics. So there's quite some math, but it doesn't necessarily mean you're going to use as much math at every discipline, every subcategory in the EM field. It depends how much. There are fields in electromagnetics that are more theoretical than others, right? And you're going to see. So let me actually, now that I have the list, you see there are like 540. These are graduate courses, but to give you an idea, 540 is fast computational electromagnetics. This is, this is math. There's a lot of math there, right? It's very theoretical. Same thing with the second one. Now, antenna analysis, that becomes more practical, right? Because it really focuses on a specific device, like the antenna, and how it radiates and how it interacts with a circuit. Radars, that's definitely more practical there. So less math, more applied. So there's a whole variety of, of interplay between how applied and how theoretical, courses can be. But yeah, math, I would say, is more important than other areas. maybe as important as, I don't know, maybe signal processing, maybe, I don't know. So that's where I left before the break. So these are the list of graduate courses. Again, there's a wide, these are obviously more focused, right, more specialized courses. It goes all the way from computational electromagnetics. So essentially this is how we solve problems in electromagnetics. All the way to antenna design, radars, microwave circuit, more advanced courses than the microwave 445 that I showed earlier. This is microwave solid state, right? Now, how can you use concepts from solid state to make faster circuits? Coherent optics, lasers, and even other more advanced, the 600 level or even more advanced topics there. So with that, I just want to give you an idea what happens after the bachelor's degree and what are your options if someone chooses to continue, and why would you want to continue. So first of all, after the bachelor's degree, we have the master's degree, Master of Science degree, and this one is a little bit more specialized. It's more specialized, obviously, than a bachelor's degree, but it's still oriented around applications, specific areas of application. Is it communications? Is it sensing? Is it circuit design, high-frequency circuit design? And then, of course, this is a very high-demand degree, especially in electromagnetics. It's very important that you gain a lot of experience. So people look a lot at master's degrees. PhD obviously is a very specialized degree. This is really, you take something very small and you work at it, very closely. It involves a lot of research and development, and that's why usually it's important if you go to companies that are bigger companies, they have an R&D department. Most of the time you do need a PhD. It's obviously a degree that you need if you want to follow a career in academia, right? Like in research or either as a researcher or as a faculty, you definitely need a PhD degree. So to go the other way around from the side of the world outside now academia, or almost outside. As I said before, if you want to work in academia, you definitely need a PhD. Work in academia means teaching, you have to teach courses, do research, so work on new topics and solve new problems or anticipate new problems that the society is going to face and try to solve them, try to propose solutions. It can involve some consulting as well, working with the industry possibly, or maybe even the government. And then other than academia, there is the area of industry and government types of jobs, right? And here you have all ranges from bachelor's, master's to PhD degrees. So now in industry and government, you're going to have the whole range of applications that I mentioned before: antenna design, communication systems, circuit design, especially high-frequency circuit design, and all the similar. This was just a list. It's not an exhaustive list of companies that typically hire in this area. So in terms of industry, I would split the industry in terms of defense companies, right, as well as more commercial companies. So defense companies like Boeing, General Dynamics, Northrop Grumman, Lockheed Martin, and then more commercially focused companies is like Apple, Samsung, Qualcomm, and this type of companies. And then there's the jobs related to government and national labs. Again, this can range all the way from NASA to MIT Lincoln Lab, different divisions in the Department of Defense, like the Air Force, Army, Navy. JPL is another type of national lab, Sandia labs, etc. There's really a wide range of government labs positions. Here is an example. Here's a list actually. So now we become a little bit more local. These are the top companies in terms of size that are hiring in the areas of electrical engineering. Intel is obviously one of the biggest. This was published actually in 2016, so maybe the numbers have changed a little bit. So we have Intel, Raytheon, Boeing, IBM, Freescale. Actually now it's NXP Actually, we also have Qualcomm here, if I remember well. So there's, especially even in Arizona and in Phoenix, there's a lot of tech companies that are coming in. There are already some bigger ones that's been here for many years, but there's more and more companies coming in. Other than the big ones, there are also smaller companies, even startup companies that do a lot of work in this area. So let me go over briefly some of the facilities that we have. So the facilities, we use them mainly for research, as well as sometimes for some labs that we do in electromagnetics. What you see here is what we call the Anechoic Chamber. This is a big room filled with foam on the walls. In order to be able to measure now different types of radiating devices, like antennas, or even measure how the signals reflect from different vehicles. So here you see like a Apache helicopter in scale, of course. So the reason we have this type of chamber is that the foam absorbs all the signals, so we can only focus and measure the signals that reflect from a vehicle or the signals that are radiated from an antenna. So it can do an accurate measurement. Other facilities include, the Wireless Communication Circuits Lab, which is in ISTB4. It's a new building built very recently. There we have a whole range of devices, from network analyzers to spectrum analyzers to oscilloscopes, probe stations to measure, circuits and on-wafer devices, contact probes. There's literally equipment that goes from DC all the way to 500 gigahertz, right? So, and then we also have facilities. Again, these are facilities that are used by other areas, but these are facilities we also use them for research and work in electromagnetics. This is the Asu Nanofab. This is a clean room facility, essentially, which is based in ERC. With that one, it has a whole range of tools where we can make devices on wafers and on substrates. So we can do lithography, photolithography, spattering, we can do E-beam lithography, and many other, high precision processes. Here's, for example, a device that we make on a wafer. There's like a silicon wafer, a 2-inch silicon wafer that has, this is from my group actually, that has, on-chip millimeter wave antennas. So, because for example, at very high frequencies, antennas become very small, you cannot really go and make them on a milling machine, a PCB board. You need really accurate equipment to go and make them and fabricate them. And then here's the list of the faculty in the electromagnetics area. So there are 5 people here. Let me go over them. Dr. Aberle, who had a PhD from University of Massachusetts. He works mainly on microwave circuit design, there's non-Foster circuits, as well as some antenna theory. Then it's me. I'm doing work on antennas. Most of them doing work on very high frequencies, like millimeter waves and terahertz. So frequencies above 30 gigahertz. So we try to design antennas on chip, antenna arrays. We try to make imaging systems, not systems that work in the visible light that we see, but in lower frequencies, so you can actually see through packaging, you can see around obstacles, all these type of applications. These are some of our work, but we can discuss it later if we have some time. Then this is Dr. Balanis. He's a very well-known name in the area of antennas. He's been many years at ASU. His main research is in antennas in general, but he works also on flexible antennas. He works also on material that we can put in vehicles to make them stealth, so they can actually absorb radiation or scatter it to arbitrary directions, so you cannot really see vehicles. Other more sophisticated concepts like high impedance surfaces. Again, things related to antenna design and scattering surfaces. And then Dr. Pan. So Dr. Pan is focusing mostly on computational methods. So what kind of numerical methods we use in order to solve the problems in electromagnetics, right? Maxwell's equations, as we said, are quite complex. So solving problems and using these equations needs a lot of work, and it requires different methods. Also, he's doing recently work on millimeter wave radars, like the radars you have in cars for collision avoidance and autonomous navigation is related to millimeter wave radars. And then finally, Dr. Palais. Dr. Palais is expertise in fiber optics and fiber optic communications, and he also is teaching all these relevant courses, fiber optics, lasers, as well as coherent optics. Here's a list of some of the books that have been written by our faculty. You might have seen them, but especially Dr. Balani's books are very, very popular. These are the antenna books that are used for courses in antennas all over the world. And it's the most cited book in antenna theory. So similar also with the book on electromagnetics, one of the most popular books. We have also books in fiber optics from Dr. Palais as well from Dr. Pan. And then here's a short list of some of the numerical tools we use to simulate, antennas, simulate propagation of signals, as well as simulate high frequency circuits like microwave circuits or even millimeter wave circuits. So with that, actually conclude my, introduction to the electromagnetics area. So if you have any questions, please go ahead. Yes.
Could you show, so what's the difference between, is there any way you could explain a little bit more in depth what each one of the specific subpaths within this path mean? Like what computational electromagnetics is versus regular other kinds of?
So let me go to this, that's a good question. So let me go to this list that has the courses, right? So the topics of whenever you hear computational electromagnetics, is essentially the methods that we use to solve the Maxwell's equations. To give you an example, are you familiar with SPICE, PSPICE, right? The tool that we use to, for circuit design. So obviously this tool has some numerical methods that it uses to find voltage and currents and what so. The similar thing we need to do now to find, let's say, how the fields radiate from an antenna. You need to find the numerical methods that will help you do that. So that area is all about what are these methods and how efficient they are. Usually the problems, the problems in these frequencies are much more challenging than in lower frequencies, like in what PSPICE is trying to do. That's why you have ADS, which is one of the tools that we use for microwave circuit design, or HFSS, which is a finite element method to find how the fields propagate in a room, or, as I said, how an antenna radiates. So that's the area of computational electromagnetics. It's a bit more theoretical, more mathematical, but it's all about numerical methods. Now there's the area of electromagnetic fields and guided waves. So this is essentially electromagnetic theory again, but it's a little bit more mathematical, and it's kind of related a little bit to computational electromagnetics. It talks about the phenomena, like how the signals scatter, reflect them in from a wall, how they get absorbed for a material, how, what are the material properties of different, objects around us. How far does the signal radiate? How does it go inside or outside the atmosphere? Stuff like that. Then antenna is another big area, right? And an antenna, you might think of it as just an antenna on a tower, but it's much more than that, because everything, pretty much every device, every wireless device, every device that's based on wireless communication needs an antenna, right? So it comes in different shapes and forms and sizes, and it comes in different frequencies. So there are a lot of challenges in designing antennas. That's another area. Then we have radars, right? Radars, until recently, they used to be something that mainly the army, the military would use, and a little bit maybe the weather forecasting guys. But now it's something that we're gonna see almost every day in cars, right? Cars need radars to be able to navigate, avoid collisions, or even autonomous agents like robots. They need radars to understand what are the obstacles around them. So it's a very big area, the radars area by itself. Microwave circuit design is now circuit theory, like circuit analysis that you do for like low frequency circuits, but this is not for very high frequency, right? So you want to design a communication system that works at 24 gigahertz. So you have power amplifiers, you have receivers, you have, I don't know, LNAs, you have a whole bunch of components. How do you put them together so you make sure they work properly? That's in that area. Then you have area of optics and lasers, right? How do you generate visible or infrared light, make it be coherent, so at a very, very, very specific frequency, not broad frequency as the visible light we have. How you make it efficient, how can you make systems, communication systems that are based on infrared or visible light. How can you design electro-optical transformers, so be able to detect an optical signal, convert it to an electrical signal, and the other way around, take an electrical signal, convert it to an optical signal. And all this area that related with how I handle optics is within that area of lasers and optics. And then so in terms of the areas that I covered through the courses, I would say these are the big main areas, if I don't forget anything. Now, of course, with a combination of all these things, you can also make systems in imaging. You can make imaging systems. You can make sensors. Navigation systems, You always need to have and combine knowledge from different sub-areas, as you mentioned before. Yes. Go ahead.
You mind if we go back to the research that you were conducting, or the subjects that you covered?
Yeah. You want? Yes.
So like on the previous page, was T-hertz is at terahertz, the little image on the left, the little black symbol?
This one?
Correct.
Yeah, so this is what I was talking about. This is an imaging system. This is a camera, right? This essentially is a camera. So yeah, I can talk a little bit about that. So maybe it's this one here in more detail. So, we're used to using cameras now pretty much for anything and everywhere, right? The cameras are everywhere. And cameras work in the visible light, the light that we can see with our eyes. And what is a camera? It's essentially photodiodes behind a lens. So they take the signal from different directions, they convert it to a small voltage, and then you put it on a screen and you see it. So this is a similar concept, but now not in the visible light, but in lower frequencies, in what we call millimeter waves or terahertz. So this camera we built in the past is between 600 gigahertz and 1.2 terahertz. That's between infrared and microwaves. That's somewhere there in terms of frequencies. So this is essentially comprised of, you see only part of the chip. This is not photodiodes, but this is antennas that are integrated with very fast diodes. And we take this chip, it's kind of the same thing actually. So we take that chip and we put it behind the lens. So this is what you see inside the camera. And then we take the signals from the antennas, we down convert them, we make them digital, we throw them to the computer, and then you see an image. Which, in this case, it's a low resolution because it doesn't have too many pixels, but you can see a cross-section of this is a pill, like a pharmaceutical pill. You can do tomography with that. In general, with these frequencies, you can penetrate material that are not conductive. You can see maybe through walls, you can see through clothing, right? So that's one of the things people do in security, right? Probably all of you have gone through these scanners in the airports. This is essentially using millimeter waves, 30 gigahertz or 80 gigahertz, to penetrate through the clothing and make an image and see if there's anything concealed, essentially. Similar things for the industry, for pharmaceutical, or anything that you can do in a non-contact fashion without opening or breaking something. Yeah.
Is there any study into the effect of EM on the human body, or just the dangers of having radiation around you?
Yeah. So, obviously, right? Because the more we have, the more spectrum we use, the more signals we have up in the air, the more we're exposed to that. So there's been a lot of research already. It's been more than 30 years now, at least on the radiation and the effects of radiation from cell phones, right? Which is in the few megahertz all the way to 2 terahertz or maybe 3 gigahertz, 2-3 gigahertz range. This is quite an exhaustive research. The findings were not alarming for us. That's why we still also have, the FCC, the Federal Commission for Communications, and every commission in the world puts limits on how much radiation any device actually radiates. So we keep it under a limit. So there's been quite some work, and there's also work that's going on for higher frequencies now, right? Because we don't have a lot of radiation now in millimeter waves, but there's a lot of research going on, or some research going on, the effects of electromagnetic waves in these frequencies. Although we don't really expect something, that's a good thing. These frequencies are actually safe to the human because they're non-ionizing. So for example, X-rays or gamma rays are ionizing, right? They go into your DNA, they break down the DNA and create lots of problems. They interact very intensely with the tissue. These frequencies, the only effect they have, at least what we know so far, is they just heat it up. They warm it up, right? But when we talk about signals that are extremely weak, the effect they have is extremely low. At least with what we know so far. But I don't think it's going to really change, to tell you the truth. Spoiler alert. Yeah.
And every time I wear an earphone and pass through the anti-theft door, those in hand, I will find that even if it's not plugged into my phone, it will sound. So that's
interference, right? So, yeah. So interference is a common problem in wireless communications. Like your device gets a signal from another device that you don't want to, for whatever reason that might be, and it's being picked up and destroys your signal. Right? That happens with in Wi-Fi. If you have in a very congested area, like many in neighborhoods that are many houses together, and you have many Wi-Fi spots, you might notice that your Wi-Fi speed really goes down. It's very, very unreliable. That's because you have too many channels, one close to each other, and one is interfering with your neighbors interferes with your channel and reduces the signal strength. Kind of similar thing happened with your earphones. You picked up a signal from magnetic door, whatever that is, and just receives and creates a false signal, let's say.
But the earphone is with string, but not that wireless one.
No, but it has a long wire that is exposed to electromagnetic waves, right? So this acts as an antenna, actually, right? So the shielding, it doesn't have good shielding. It doesn't shield itself very well to the ambient electromagnetic waves, and that's where it picks it up. Yeah.
Going off that same topic, what would be properly to actually seal that, like you said? Just if it was regular headphones, would the actual plastic coating not be sufficient?
No, plastic is not good. Usually when we talk about shield, you need to put a metal, because metal is something that blocks electromagnetic waves, right?
Specific metal?
Well, the cheaper the better, I guess, because most of them are good conductors. So the thing is how you do the shielding is the problem. Like how you put and where you put the metal is important. But if you put the metal, you make it bigger, you make it heavier. So there are other problems that come with shielding, cost, all those things. Yeah.
As I go through my EE coursework and I hear terms like microwave and optics, should I disconnect that from the actual microwave in my kitchen, or?
No, it's.
Or is it related at all?
It is, yeah. So, so the term microwaves, how the term microwave came from, they first started using high frequency signals in the Second World War. That's when they first made the radars. They made very high frequency signals so they could actually detect ships and stuff. And these were very small wavelengths, and they called them small waves, microwaves. And that's how they came with the term. Now these signals, we use them later now to just warm up our food. So the microwave oven works at 2-point-something gigahertz, which is part of the microwave spectrum. And that's what we call a microwave oven. Now, microwave circuit design is essentially designing circuits that work within that range. A little bit lower as well, a little bit higher, right? It's not just where the microwave oven works, but a much wider spectrum. But optics is a different story. Optics is much higher frequency signals, right? And theory is a little bit different. We don't have circuits in optics, right? We don't have circuits there because conductors don't conduct in the optical region. Right? The metals are not metals anymore in the visible, in the optics region. So there's a different story there in how we design devices that work in optics. We don't have wires, but we have waveguides. Right? So an optical signal can propagate through a fiber. Fiber is what? It's just glass. Very extremely thin glass, transparent, allows the signal to just bounce back and forth, up and down into that glass, tube, and go to the other side. But it does not. Optical signals don't penetrate, propagate along metal wires, as they do their microwave counterparts. So, parts of the electromagnetic spectrum, but the way you study them, you design systems on them, different principles, different theory.
Thank you.
Yeah. Yeah.
Where are you from?
I from Greece. Came from Greece. Yeah. Yes, I know. I do. Xero. You know, huh? Nice. Yeah. Yeah. Any other questions? Have any of you taken 241 already?
We're in it.
Nice.
Right now.
Sophomore? You sophomore now, he said?
No, we're juniors.
Okay, that's okay. Yeah, again, I know, guys, 241 is the very first course you get exposed to electromagnetics, but I need you to think like beyond that. Things that you can do with electromagnetic waves. It's a very broad area, right? It's not just about the tensor that you see in 241 or the integral. It's much more beyond that. And you have to know something. People that go in electromagnetics, maybe because not too many people go in electromagnetics, it's an area where you also don't have as much competition, right? There's quite a lot of work, a lot of opportunities there that really are left. Mainly because sometimes people think that, electromagnetics is too hard for me and, I cannot do that. I'm just going to go do something else. Don't think of that. Think if you enjoy the area and the applications and the devices and the systems. Don't think, oh, it's too much math and, Okay, if you really hate math, I don't know. If you really hate math, yeah. But think a little bit beyond that, right? All right.
Thank you for your time.
Thanks for your time as well. And again, if you have any questions, guys, you can just, find me, email me, or whatever. Okay? Good luck.